Hello and welcome to the presentation for the SIGGRAPH 2021 Emerging Technologies paper titled Health Greeter Kiosk. My name is Max Hudnell and I work at the UNC Reese Innovation Lab alongside my co-author Stephen King. To start off, the Health Greeter Kiosk is a form of digital signage to promote face mask use and social distancing. We started working on this technology at the start of the COVID-19 pandemic when the World Health Organization recommended wearing face masks and social distancing as the two main methods which can be used to minimize transmission of the coronavirus. Typically, physical signage is used to instruct people to put on their masks and social distance. However, we found the problem that physical signage typically isn't very engaging and can go unnoticed. So to create a more engaging form of signage, we came up with a visual feedback system which integrates real-time face mask and social distance detection. So you can see on the right, graphics are drawn over the face and chest, which indicate whether you are or are not wearing a face mask and whether you're too close to other people. A secondary goal of our work was to come up with a stat collection system to collect stats like the percentage of people not wearing masks or the number of social distance violations which occur over a given time span. Stats like these can inform facility owners as to whether people in their building are being safe and following the rules. Final goal of this project was to maintain a low budget. In terms of money, the cheaper the kiosk is, the more kiosks which we can produce and potentially the larger influence it can have. And in terms of resources, the less resources it uses, the less energy it will draw, which will allow us to deploy the kiosk outside and power it off of a portable battery. Specifically, we did not want to have to use a GPU since this would greatly increase the cost of the kiosk and the energy use. I'll now briefly go over some of the research background for the technologies we use in the kiosk. Face mask detection is typically performed via supervised learning, where you train a model by showing it lots of examples of the type of data you want it to learn. One dataset that gets used for face detection is the wider face dataset. This isn't specifically for face masks, but it does include images of occluded faces, which is useful. There's also the MAFA dataset, which is specifically for face masks and includes images of people wearing masks correctly and incorrectly. And more recently, there is the masked face net dataset, which is even bigger and gives even better descriptions of their data. In the case where a mask is being worn incorrectly, it'll tell you which specific part of the face is exposed. The types of detection networks for face mask detection is still an active area of research. Last year, AIZ Tech released a model based on a single-shot detector, which is lightweight and capable of running in the browser. Other researchers use a ResNet feature extractor paired with SVM and YOLO classifiers. These models are highly accurate, but not quite as fast as the SSD method. To perform social distance estimation, you need to solve two tasks. The first is person detection. This is often done via a bounding box predictor, but to calculate a distance, you need 2 points. So people often take the center of the bounding box to represent the central coordinate for that object. A better solution is to use a body pose estimator, which outputs key points directly corresponding to joints on the body. So we're able to just take the chest key point and use that in our distance calculation. The second task you need to solve is scene geometry understanding. After you have a 2D key point, you need to get 3D information for that point. And if you just have an RGB image, this can be a lengthy process in which you start by estimating the ground plane and then project your key point to the ground plane. And then you establish a metric reference so you have a sense of scale in the image. However, this process requires making a lot of assumptions. For example, when estimating the ground plane, you might assume that you can detect a rectangle on the ground, or when projecting to the ground plane, you might assume that you can detect the feet of the individuals. And when establishing a metrical reference, you tend to assume something about the size of the object you're dealing with. Like you might assume the height of a person to be 5'10", which obviously isn't correct in all cases. So instead of going through this process and making all of these assumptions, we choose to use a depth sensor where we don't have to do any of this and can just acquire 3D information directly. The only downside about using a depth sensor is that it can be costly if you need long range estimation. However, we just need short range, so we can use a relatively cheap one. As you might imagine, there are a lot of related products which are similar to our kiosk, so I'll try my best to explain how we're different. First, there are sign-in kiosks which check if you're wearing a mask and check your temperature before you're granted access to a building. However, these don't perform social distance detection. There's also entrance flow management systems, which encourage face mask use and social distancing as you wait in line. However, these typically rely on physical signage like stickers on the ground or a stoplight telling you when you can move up to encourage social distancing. There is some software which actually performs social distance detection. This is typically used for security cameras. However, this is a different use case since this is from an overhead or high viewpoint, where our kiosk uses a slightly above eye level viewpoint. There is one system which is most similar to ours and uses the same viewpoint, which is released by Amazon, and they use an RGBD camera and also have visual feedback. However, their system has no face mask detection, and it also requires a GPU, which greatly increased the cost of their system compared to ours. I will now describe our method. The main component of our design is a live stream video which acts as a digital mirror for whoever stands in front of it. The motivation behind this design is that it would lead to an increase in self-awareness, which will then lead to more responsible behavior and better compliance with the mask and social distance mandates. There are mask indicators, which are shown as graphic overlays over the face. And there are also social distance indicators, which are drawn over the chest and turn red if you're within 3 feet of another individual. There is also a privacy statement at the bottom of the screen, which we included because after some initial testing, there were some privacy concerns, so we just wanted a clear statement saying that video is not recorded or transmitted from our kiosks. For our face mask detection network, we used the model publicly released by AIZootech. Their model is a modified single-shot detector in which they replace the backend with a light version consisting of only 8 convolutional layers. The model has an input size of 260 by 260 and a total of 24 layers. They train their model on about 8,000 images from the wider face and MAFA datasets. Now, this model outputs detections on a frame-by-frame basis, but for our purposes, we need to track these detections by assigning them an identifier and following them as they move across the screen. To do this, we use the popular sort tracking algorithm. This enables stat collection on a per individual basis rather than a per frame basis. And because the underlying mechanism of sort is a Kalman filter, we're able to use that for free track smoothing, which makes the tracks look less jittery as they move across the screen. Social distance detection is a multi-step process in which the end goal is to obtain a 3D coordinate for each person on the screen. The first step in the process is to acquire 2D body key points for each individual. We do this using the lightweight open pose network to perform body pose estimation. This network is based on the popular open pose algorithm, but it is optimized for real-time performance on edge devices. And from that output, we only keep the chest coordinate for our calculation. The next step in the process is to deproject the 2D key point to 3D. We do this by using our 3D information captured by our depth sensor. The final step in the process is to then estimate the social distance by using Euclidean distance in the calculation. Note, in this example, since there are only 2 people on the screen, the distance between them is stored as their social distance value. In the case where there are more than 2 people on the screen, the distance to someone's closest neighbor is stored as their social distance value. We collect stats relevant to both face mask usage and social distancing. For face masks, we count the total number of individuals wearing masks, as well as the number of individuals not wearing masks. For social distance, we count the total number of individuals, as well as the number of social distance violations which occur. And we also calculate an average social distance value for each individual. This value is maintained as a moving average as a person is tracked across the screen, and the update step for the moving average is shown at the bottom of this slide. D in the formula is the social distance value for a person for the given frame, and N is the total number of frames for which that track has existed. This average social distance value can be aggregated amongst a group of individuals over a period of time to give a more general statistic saying how well people are social distancing in a given area. Now I'll go over some of the implementation details. For our hardware, we use an Intel D415 depth camera along with a Lenovo M90N Nano computer to do all of our processing. This computer is equipped with an Intel Core i5 CPU, and it runs the Ubuntu 18 operating system. Our computer vision pipeline is a multi-step process. The first step is frame acquisition, in which we acquire the color and depth frames from the Intel RealSense SDK. The second step is image preprocessing, in which we align the color and depth frames and also resize the images so they're compatible with the networks, and perform a horizontal flip of the image to give our kiosk a mirrored effect. Step 3 in the pipeline is to perform model inference on the face mask and human pose estimation networks. Inference is performed asynchronously up to 2 frames at a time, or since there are 2 models running every frame, this means up to 4 models can be running simultaneously. We use the model optimizer to convert the models so they're compatible with the Intel OpenVINO inference engine, and this gives us optimized CPU inference performance. Step 4 in the process is post-processing, in which we perform object tracking, social distance estimation, and our stat calculations, and we draw graphic overlays on the image. Step 5, we send our calculated statistics to a backend Django API where the stats are stored in a database, and we perform this step every minute or so rather than every single frame. And the final step in the process is to send the frame with our graphics drawn over it to the local web server, and we utilize local sockets to do this. Additionally, all of this is done in a single C++ application, and all inference is done on the CPU with no GPU being required. Optionally, you can offload some of the inference to an Intel Neural Compute Stick to increase performance. All in all, our computer vision application achieves a frame rate of 26 frames per second, or you can get an additional 2 FPS if using an Intel Neural Compute Stick. The responsibilities of our local web server include receiving processed video stream from our computer vision application, and then streaming that video to a URL endpoint. It's also responsible for hosting the HTML web page, which is used as our kiosk's display. And we use the Flask Python web framework to do this. We've tested out our kiosks via various deployments. We've tested on a college campus where this spring semester at UNC we've deployed in 7 buildings near the entrances to remind people to wear their masks as they walk in. We've also deployed at public events such as UNC football games and UNC graduation, where we deployed the kiosks near entrances where people line up to remind people to wear their mask and remain distant as they wait in line. We've also deployed in the corporate office setting at the Lenovo US headquarters located in the Research Triangle Park of North Carolina. And through all of these deployments, we've observed higher engagement and better persuasiveness when compared to physical signage. In summary, the Health Greeter kiosk is a form of digital signage which promotes face mask use and proper social distancing. and it does this via a visual feedback system which alerts pedestrians when they violate these protocols. It integrates real-time face mask and social distance detection at a high frame rate of 26 FPS, all without the need of a dedicated GPU. We've also built a stat collection system which informs facility owners of face mask and distancing trends at their facility, and it enables them to make smarter decisions during the reopening process. For future work, we'd like to pursue a more formal study comparing the effectiveness of the HealthGator kiosk versus physical signage. We'd also like to try out other methods of visual feedback or even auditory feedback. We've experimented with some of this already in our concierge mode, which is shown in this video here, where a digital concierge provides verbal feedback.
I'm glad you're here, but you forgot your mask. Welcome, and thank you for wearing your mask.
Thank you for watching our presentation. If you'd like to learn more, please attend our Q&A at the COVID-inspired innovation session. Thank you.